Sorry, it's taking forever to log in my account. Just to be sure, this is a math class, right?
Yeah.
Okay. Oh, well, it's taking very long. All right, let me try and start from memory, so we're stuck with Windows. All right, so I don't know how you think we should go, but I like going this way, using this, and then I produced a set of slides that's just a perfect copy of what we've been saying, and you know, if this can solve many things very fast, then you know, writing a lot of matrices can be quite tedious. So this is an experiment. I've never taught in person using this, but since it's arriving, right? So well, I'll continue try and do that. And if you don't like it, tell me. And I'll change.
Is there a date set for the midterm?
Yeah, I think it's in the, so it's quite late. It's after the break. So yeah, I think it's the first class after the break.
Or is it early March?
Yeah. Yeah, so it's going to be, yeah, I had the choice either to set it before or after linear algebra. I thought let's have a linear algebra inside it. So it's like a big chunk of material. Wow, internet is so slow. Next time I'm going to bring two computers, it's going to be better. I remember what I want to tell you, but yeah, it's better to not start on a tangent. Anyway, so what we're seeing today. Okay. You ever seen this? Like 10 minutes to open it? Come on. Unusable. Oh, it's like being back in the 90s or something. Like they have no yeah, that's why I like preparing in advance. Hopefully we can prepare in advance next time. Like there's nobody that has ever used this computer for some reason. Anyways, if some people are less, they can arrive. Yay, more people. Okay, so we haven't started yet because this has like 1 RAM of 1 gig of memory. Maybe I don't know, but it took forever. So as I was saying, I kind of like teaching this way because my handwriting is so bad that you just wouldn't like it. So I think this is fine since it's working. And yeah, and I'm taping this. So if you're sick, you don't have any reason not to watch. But please, if you're not sick, please come. It's better to have people here. All right. So yeah, and I don't have anything else to say. So we continue chapter 4 today. And now we start the interesting stuff. Vector products and matrix products and all the fun that's coming with it. Yeah, I'm stuck with this bar, so I'll see if I can sort of not show it next time. Oh yeah, it's very nice. Nobody knows if I can hide that. Yeah, that's life. We're stuck with it. All right. Oh, this has just disappeared. Hi, vector products. So let's have, yeah, 3 by 3 vector is nice. Yeah. So let's start with inner product. Yeah. So consider. I'm going to have two vectors. And yeah, just to not have any problems, let's just use 2 by 2. So V1, V2. And W, W1, W2. So now I'm going to try to explain a bit why we do multiplication as we do, because up to now, so addition, subtraction kind of makes sense. You have two vectors that have the same size, so you just add or subtract their members, so that, or two members or two matrices, that's not too complicated. But then multiplication can become a bit more involved. So we have two ways of doing multiplications. So let's go with inner product first. So inner product, you would write it this way, V prime W. And so if I write it this way, it's so it's the same symbol as I was doing using before for transpose, and it's not an accident. It's because I cannot multiply, I cannot take this product, VW. This is impossible. So don't ever try this at home. It's not going to work. So what you have to do is first take the transpose of this vector, or take the transpose of that vector. So if we start with the transpose of this vector here, then we get the inner product. So if I get P1, P2. Oops, it's a vector, sorry about that. Times W. And what I am going to do is to multiply member by member. So the first element of the vector V is multiplied by the second element of the vector of the first element of W, and same for the second element. And then I add up all of them together. So then what do I get? I get V1, W1 plus V2, W2. So I get a scalar. And some people may say, do I get a scalar, or do I get a one element matrix? So I could say what would be the problem with the one-dimensional matrix is that, so if I have just a scalar, as I was saying, if I have C that multiplies this, then I get CV1, CV2, and it's fine. So if I multiply by a scalar, it's fine. But as I just said, so if I have C that's a matrix, it doesn't work. C has to be a vector, and the vector has to have the same number of columns as the second one has number of rows. So yeah, I won't blame you if you write it one way or another, but just this is perfectly fine. So just say it gives you the sum of the multiplied elements there. And one way to write it with sum. So why did I spend some time with sum? That's because it's very useful to use sums here. So here it's just with two elements, but we could have done it with many elements. So VI, WI. Then important note, both vectors must have the same, or if I don't take the transpose, must as many columns as W as rows. All right, so that's conformity, and we have to do that. So let me try and convey to you why doing this operation would be useful. So imagine that you have many different goods and many different quantities. So for instance, you're dealing with budget constraints. So example, so total spending on two goods. With prices you want two and quantities you want. So then what is my total spending? So the total spending is P1. Let's write this M for my budget, for instance. Q1 plus P2 Q2. But then what I could have done is, so here this is I know these are prices and I know these are quantities. So is there a nicer way to write it? Well, yes, I could have just said this is equal to, say, P1 P1 P2, and then Q1 Q2. And this would have been, so you would write this in a very compact way as PQ, where P, or rather you would write it, yeah, P prime Q, where P is and Q is Q1, Q2. Right, so that's a very neat way of representing a whole bunch of information with very little. Oh, by the way, can you hear me well at the back? Yeah, okay. If not, please tell me, and so I might forget. All right, so this is inner product. And now I've told you that, so to get the inner product, what I first needed to do is to take the transpose of the first vector here, take V prime. But then there is another way of multiplying vectors, which is to leave the first vector as it is, but take the transpose of the second vector. And then you get something entirely different. So let's show this outer product. Yeah, so I don't know if I have a good trick to remember what is inner, what is outer. So as you're going to see, inner gives you essentially a scalar, one-dimensional thing. So here it's just a sum, and you're going to see that outer gives you a big matrix. So I don't know, outer like big, or I don't get your own trick to remember. I don't remember. So it's and it looks somehow like the Cartesian product that we've seen. So in the following sense, so how would you write it? You would write it this way: V W prime. And then, so you have V like this. And then you take the transpose of W. So W1, W2. And what you do for the result, you get a 4x4 matrix. So here you realize that however many elements I have in my first vector and second vectors, all I get at the end is a 1x1 thing or a scalar. Here the dimensions, but there is one restriction, is that they need to be able to conform with each other. In this case, I can have any dimensions I like, but I'm not going to get a one-dimensional thing. I'm going to get a matrix, 2x2 matrix. And here what I do is I combine all the possible, I take all the possible combinations of the elements from each vector. So here I get 1, W1, V1, W2, V2, W1, and V2, W2. So this is, it really looks entirely different, but you could still have situation in which such a thing is useful. So I have my idea of this is, imagine that it's only a single good. It's not different goods, but say the quantity varies, and so the time of the year varies, for instance. So how would you write this? So yeah, example. Spending on one good, but with what did I read here? Prices that vary during the week, and quantities that vary between seasons. For instance, we would have P equals 1, P2, 3. And we would have, say, Q. So what I said, quantities vary between seasons. So I could have, for instance, Q, oh yeah, so P, I said during the week, so let's have Monday, Wednesday, and Thursday, and Friday. Just to show you that it really doesn't matter the number, it depends what you represent there. So this is price Monday, price Wednesday, price Friday. And you could have, say, quantity summer and quantity, yeah, let's use all this. And quantity, so W, it's there for, so winter isn't good, fall isn't good, spring isn't good. So yeah, do I have nothing else? Spring, summer, fall, or winter. So let's use F, I don't know, doesn't matter. I just wanted to use a different letter. So what would I get? I would get that here the product would be P2 prime equals is multiplied by, oh yeah, I've already written it this way, sorry. Didn't mean to write this. QS, QF, And I think he's going to be nice with me. Yes, here it is. So here, what do I get? I get a matrix of all the possible endings. Then good. We have, yeah, Monday's price with summer quantity, Monday's price with fall quantity. Yeah, and now he's changing my order for some reason. Yeah, and Wednesday's price, etc., etc. So you see that this is a way to express all the different sort of information you could get from different combination of things, and quite efficiently, I might add. All right, so that's about it for vectors. So we have a quiz on vector. Can I get the link? Ah. Yeah, it's that. Yeah, so you can do a small quiz on vectors. Yeah, I'll paste it later. Okay, and with so questions about this. So it's you have to remember the procedure, how to do it, learn it by heart. It's going to become second nature. So I asked last class how many people had already seen it, and like 2-3 people said yes. So now I have more. So for who has already seen this? Okay, so yeah, it's for you, it's going to be easy, so you can relax a bit. But for the others, then buckle up. Yeah.
Normally vectors, there's two types of direction and dot, yes.
Oh, so now you're talking about the graphic interpretation of vectors.
Yeah.
So yeah, it's not so useful for. I might talk a bit about it, but so go ahead with your question anyway.
Because I'm used to thinking of like when you multiply two vectors, you get a vector as a result, right? Like, whereas I'm seeing this as more of a matrix from a vector. So like when you have like two vectors that produce a matrix, like, that's a bit different to me. But other than that,
Yeah. So sorry if I'm confusing people who are more used to. So if you have done, say, physics, for instance, it's completely different. So as I said last class, I'm going to assume that a row vector is a matrix with a single row, and a column vector is a matrix with single column. But so there are all matrices in a way. But I'm going through this just to set it up for the multiplication. That's coming. Okay, so general. Yeah, so it's good to have you there so I can really yeah, interact more. So to multiply. Matrices A and B. So they must have the appropriate dimensions. So here I'm going to write so A times B plus C. And I'm going to see that A has dimension A n times 10. P times dimension N times P. And then C is going to have dimension M. So how do we do that? So each element ij of the resulting matrix C is the inner product of the row I matrix A with column G. Matrix. So before writing just a big thing, I'm just going to do it in front of your eyes. So it's the combination of inner and outer product all together. Yes, we can do that. So imagine I have A, B, C, that multiplies. So what do we get? We get. Okay, so inner product of first row with first column. So I get what? I get A times E plus B times G. Here I take the inner product for, and I multiply the element of the second row with the first column again. C, E plus G. And then the F, A, F plus BH. And C plus hope I didn't make a mistake. Just verify. And then for a general matrix, so if I had more elements in A and B, then I would have that C is now. So good luck if you want to copy all of this, but yeah. Let's go with 4, 4. So this would be the sum of J equals 1 N of A1 J times B. Yeah, so yeah, so this is the different from this. This is just an example. So I'm going back there and BJ BG1. So here, this is with row 2. So I changed A for 2. And this is row, yes, I'm going to say this as N by N and N by P. So this is N. Then same thing, but the second column. Will be 2. And then the last column is Here I have element. All right. And so let me make this fancy. So this is the whole general, and you have a very neat, compact way of writing it. So I could also say that C is simply equal to the matrix, which is made of these cells there. So I can take one cell, for instance. So this is, but then I replace, this is I, this is, what did I write here, K. So it's going to be true for any of, so I'm just always synthesizing information more and more and more. And here, all I'm saying is I can define my matrix C very succinctly this way. So it's made of sums. And of course, for I equals 1, 2, n, and J equals P. And this representation is going to be super helpful for all the proofs we're going to do. You can, because matrices can have as many numbers as you want. So if you want to start proving stuff, and you write them this way, it's feasible, but you just you die in the process. So, but if you can write them this way, it's super helpful. All right, note about the dimensions. So 2D conformable. This is how you write it, right? For multiplication, the matrix A the same number of columns. And here we said that, so that number was n. Say that? Oh, it's too small? Okay, yeah. Let me try. 150%. That better? Anyways, of course, I'm going to post this online, but if you like copying it, I don't mind. I don't know what my opinion is about copying. In a way, it's good because it forces you to be active, but I don't know. Sometimes I'm just desperate to copy everything, and and I don't understand. So. Yeah, so that's one thing. Oops, sorry about that. Tell me when you're done with the, okay, I can write it here. So the resulting matrix has dimension as the same here. As X, which is n, and the as oh, sorry, not X, but A as B, which was P. So this is, of course, what we did write here. So we start with m times n times p, and we finish with m times p. So this is something, a neat trick to remember. So it's sort of the author is what allows you to know what are the dimensions. So you know that you start with a matrix A that has m rows. You're going to have m rows at the end, and you end with a matrix P that has p columns. You're going to end with a P, and then everything that's in between has to be the same. So here the number of columns of A has to be equal to the same number of the readers. Yeah, exactly. So columns of A has to be the same as the rows of B. So this is a neat way of knowing if it works. So you start with M, you end with M, you end with P, you end with P, and everything in between is stuff that has to be the same. So now I had a very nice explanation of everything. I'm wondering if it's useful to explain it. Check it. So is it confusing for you, or does it ring a bell? Anyways, I see that most of you have already done it. So if you were really beginners, I would spend more time, but I think I'll move on a bit. One comment I had, so the product is also the summation of outer product. So you can say that it's either the outer product of inner products, but also the summation of outer product of vectors. So vector, say that the first vector is A's first row, and then the second vector is A's second row, and etc. So I'm not going to say more about this, but it's just if you like to think a bit about what's going on. And this matters when you go into stuff like computer science, and especially stuff like sparse matrices. Some operations, when they are dense, so dense matrices are matrices that have non-zero elements everywhere. So you can do them this way. But if they are sparse, there are algorithms by which it's much better to compute them as outer product and then add them together. So that's if you're interested in sparse matrices and computer science, I'm not going to say more on that topic. Yeah, so okay, aside. Sparse matrices are something like so then you have one element there, and then one element there, and then 0.1, and then the rest is just 0, 0, 0, 0. Yeah, and if you just multiply it very like this way, all you're doing is going over all your matrix and adding zeros and zeros and zero, and it takes a lot of time. Whereas this, you could just say, I have a matrix of 0, but I have one non-zero element at 1, 1, one non-zero element at 3, 2, and one non-zero element at 4, 1. And you've represented your own matrix with this. So, if you hear about but this is by no means on the exam, don't worry about this. If I put it in parentheses, yeah, it's an aside. Okay, so just to practice a bit, so think about so if I have A equals so yeah, 2, 3. B is ABCD. And C is gamma, my favorite number. Oops. So please compute the following. AB BC AC CA. And do I have any? No, that's about it. Yeah. Oh, these are enough. So I give you a few seconds to do that, just to, if you've already learned that, then it's no big deal, but okay, we can go ahead. So what's the dimension of AB? Yeah, 1 by 2 exactly. So I just look at what the dimension of A is, it's 1, and what the last dimension of B is, it's 2. So I get 2A plus 3C, and then I get 2B plus 3. Okay, another person, the dimension of BC. Yeah, 2 times 1. So it's A gamma phi. And I have C plus AC is what's the dimension? Somebody else? No clue. Well, I said you could either say that it has dimensions or maybe it's just a scalar. Yeah, so AC is just it's like A is like as I said, I'm going to say it's the vector and C is a vector, so it's just an inner product. So you get 2 gamma plus 3 pi, and then CA is an outer product. So yeah, I'm too lazy. All right. So any uncertainty about this? So it's you just learn the procedure, you do it, practice, and it becomes second nature. And by the way, so later on, you're going to see that you don't you have to know how this works, but you don't necessarily do them a lot. What you do is manipulate matrices without even having to look what's inside it. So you just have to make sure that they're the right dimensions. But then since you know properties about them, you know how to manipulate them. Okay, oh, it's, yeah, we're still halfway. So have another quiz there. Yeah, I'm going to put it, so 2 quizzes for the price of 1, I think. Properties of matrix algebra. Here maybe it's going to be a bit more painful, but hang on. Properties of addition. And especially, so commutativity of addition. So we have that if I have a matrix A plus matrix B, then it is equal to the matrix B plus the matrix A. And then I can just have some very intuitive demonstration of this. So you just express it as A ij. And here I could add commas, but I'm not going to. Plus B ij. So as we've been saying, it's equal to each element of the resulting matrix is going to be simply the sum of the corresponding elements for the first and second matrix. So it's just going to be Aij plus Bij. So if I ask you to prove stuff, please do it as well as you can, and please justify as well as you can. But my part of the bargain is I'm not going to ask you very hard things. Well, proving things well can be challenging, especially if we're not used to. But in economics, if you go on later and you write papers, sometimes you have to prove stuff. So it's good to just start flexing your muscle early. So here is how I would do that. So you could even write something like addition of matrices, but I'm not going to what's good is to show where the magic happens. So where you come up with the important property that allows you to show stuff. And here that would be simply this, and this would be commutativity of scalar addition. And then that would be equal to so here's how this notation is so useful, because I'm not messing up with dimensions or yeah. So of course I have to so the dimensions of A and B have to be conformable. That's for sure. But you see that, so I could say for sure, of course, this, but once you know that, then just using this small notation there allows you to prove sometimes very challenging thing to think about. Second property. So questions about this? And also, yeah, when I say prove things, so the reflex that we all have is to say, yeah, I have no clue, but what I'm going to do is look at some other proof that looks a lot like it, and then try to adapt it to what I have to prove now. So sometimes it's going to work, sometimes it doesn't work. It depends what I'm asking you to prove. Yeah, so right away this is yeah. So again, I'm not a mathematician, I'm an economist, so I probably a mathematician would think what I'm doing is sloppy, but I want to help you as much as possible, and I think sort of introducing a bit the notion of proof is good, but yeah, going over all the, so is the result unique, is the result blah blah blah, blah, and so we're not going there. So yeah, so doing it this way is good. Yeah, you don't have to say, oh, for A with member of R, B member of R. At some point, it's I'm going to be happy with this. So yeah, associativity of addition. A plus B plus C is equal to A plus B plus C. So I could just let the proof to the reader, but let's go ahead anyways. So this is a real case in which you can see what you have to work with. Oh, I just did something that that took this notation, and then I used some property for scalars. So maybe I can try and cheat and inspire myself from this proof and see if it works. So how would I do that? Well, I would write something like this. So I would have A plus B plus C, which would be equal to A plus B, a matrix A plus B plus C. And then what is this equal to? It's equal to, of course, element by element. So I take the elements of this, I add them up to this one, the Cij. And yeah, what I could, yeah, so if I want to be really formal, I think this is better because I'm really highlighting the fact that this is a, so people take for granted that that addition of scalars is associative, so we just get rid of parentheses. But since now the argument is about associativity, I think it's good to keep them. So these are the elements of the first matrix, and this is the element of the second matrix. And now, of course, this is equal to A plus B plus. And this is the SSE. And then yeah, so even if something looks simple, thinking about a way to prove it is not necessarily easy. But once you see it, you can go through the steps and think, oh yeah, it makes sense. But yeah, I totally agree if you think that it's non-trivial work to do that. All right, so matrix. Yeah, commutative. Matrix multiplication. So A B equals B A. We can do it the same way. Nobody's stopping me. Please, somebody stop me. Yes, okay, good. Yes, matrix multiplication is not commutative. I had a colleague who would go on for 40 minutes and wait for and say completely outlandish stuff and wait for a student to say, I think it's not exactly true. And but yeah, that's the risk. If you just keep on going and nobody stops you, you're in trouble. Anyways, so matrix multiplication is not commutative. So AB does not equal BA. And we can prove things that are true, and we can also prove things that are not true. I told you what's the best way to, or what's a good way to prove that something is not true or not true all the time. Yeah, counterexample. So let's go with one. So, and of course, if the dimensions are yeah, you can pretty much know that since we, so if we start with, say, 1 by 2 or 2 by 1s, you get different things anyways, but even if they are 2 by 2, we can show that they don't work. Question? Oh yeah, exactly. So, okay. So this counterexample. All right. Yeah, so they are yeah, they are not 2 by 2. I just wanted to show that even 2 by 2 doesn't work. Or n by n. So if I have
It was a unit matrix, like 1, 0, then does that matter? No.
1, 0, 0,
1, 0, 0, 1. So
if identity matrix, yeah. So yeah, that one would work.
that's
So
the only case that
not so if you have 0, 0, 0, 0, it works.
Oh,
too.
yeah, that's
Yeah. So you have a bunch of them. So so the name is ident, but then idempotent matrix
Yeah.
are exactly this matrices that. Oh no 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 no, it's not the same. Idempotent is you still get the same thing. Yeah, sorry. So yeah,
Is your matrix or identity matrix would work, but other than that, it's not.
yeah, I think so. Maybe I wrote it later. I don't remember. Anyways, so I'll take your word for it. So AB CD times EF GP. So the first element is, so you don't just have, yeah. So here we get A E plus B and other stuff. And of course, if I flip them around, then I would get EA. So that's the same, but CF, which is totally not the same. So you really see that. Anyways, we could see that there was not a lot of hope. All right. Distributive law. So if I have A, which, so I'm going to have dimensions here. So A, of course, so this gives me, so you can see that it works because at least the dimensions work. So I get AB plus this. So now proofs with multiplications get interesting, to say the least. Should I go through them? What time? 2:25. Yeah, so I can, let's finish with that one. All right. Oh, I have people who are tired. Yeah, no, let's do that one. A times E plus equals A times, and I'm going to have my single elements. JK plus JK. J is 1 n, and K is 1 to P. And then what can I do? So I just take the multiplication. So what do I get when I multiply two things? Oh yes, so this is, oh sorry, that's not. So I just use the definition of multiplication, that's it, which is this. So this is the expression of a multiplication of two matrices. So here are the elements of the first matrix, the elements of the second matrix. So I can use this. So yeah, I'm going to get a big matrix with which are going to be J n of Aij. These are the elements of the matrix A that multiply the elements of the second matrix. Oh, yeah, no, this was fine. Sorry. Yeah, it was fine. This is the second matrix. And then you guess what's coming. I'm using the distributivity of addition. So I'm going to get, and this is a property we've seen last time, with that works perfectly well with summations. This is equal to PB plus. So I went a bit fast here. So what you have to see is AI will give me all the rows of the resulting matrix. The K's are the columns of the resulting matrix, and the J are the indices I use for the addition for the inner product. And since I can, yes, since it's just an addition, then I can just separate the two of them. That's feasible. Yeah, and maybe all right, so I'll just write the last property, but not prove it. And by the way, I haven't found any proof of it. It probably exists, but I had to figure it out for myself, and it's not easy, but it's feasible. So last property, associative law of multiplication, which is the following. So I have three matrices. A times B times C. And here, this is, of course, or rather, I'm going to start with the first. So N times P, and then I have to have P times something else, P times Q, which is equal to A times BC. And you can just write it very succinctly, ABC. And as long as they are confirmable, then that works. So here I have N, and N, P and P. So that would be the same as N and P and P. And the resulting matrix will have the dimensions N times Q. And I'm going to write what you may find in articles. The proof is left to the reader. As the proof is trivial and left to the reader as an exercise. That's the appropriate way scientifically to be lazy. Okay, so I'll stop here for now. And yeah, so we're going to continue next time. I'm going to post the quizzes, and I think the homework should be mostly close to being finished. Yeah, and good luck with the TA, and have a nice weekend.